Hello everyone and welcome to the second hour of capacitance. In this hour we are going to focus on series and parallel combination of capacitor and insertion of a dielectric inside the capacitor. So without wasting time, let's start learning capacitors in series and parallel as our first thing. So let's say we have got capacitors in series and parallel. If we have got multiple capacitors in series, when they are connected in series, the important condition to remember is that they are in the same line. So the same current flows through them. So the amount of charge flowing through them is same. So same charge flows through them when capacitors are connected in series. If initially all the capacitors have the same charge, then at given instant of time, since the same amount of charge flows through them, they will have the same magnitude of charge on them. Now, if you wish to replace all these capacitors and wish to place a single capacitor, and you will call this single capacitor the equivalent of all these capacitors. So what is the formula to find the equivalent capacitance of all these capacitors connected in series? You will say that the equivalent formula looks exactly like that of resistances in parallel. If you have got multiple resistances connected in parallel, then the formula to find the equivalent goes like 1 upon R equivalent equals to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. Similarly here, 1 upon C equivalent equals to 1 by C1 plus 1 by C2 plus 1 by C3 and so on. And all the important points which we have learned about resistances in series and parallel work here as well. For example, I told you guys that if you have got two resistors R1 and R2 in parallel, then the R equivalent comes out to be R1 R2 by R1 plus R2. Similarly, if you have got two capacitors C1 and C2 in series, then you will say that the C equivalent is nothing but C1 C2 upon C1 plus C2, because the formula of finding the equivalent of the capacitor in series is same as the formula for finding the resistances in parallel. Moreover, we have learned that if we have got multiple resistors in parallel, then the equivalent resistance comes out to be lesser than the least of them all. Similarly, if you have got multiple capacitors connected in series, and let's say these capacitors are of 2 farad, 8 farad and 22 farad. Without even raising pen, without even solving, I know that when I find their equivalent, the equivalent will be less than the least of them all. So the equivalent of these three capacitors must be even less than 2 farad. I can even say, if you have got n identical capacitors, each of capacitance C connected in series, then the equivalent capacitance will be same as that of n identical resistances connected in parallel. When you have got n identical resistors connected in parallel, the equivalent resistance is R by n. If you have got n identical capacitor, each of capacitance C connected in series, then the equivalent capacitance is nothing but C by n. So these are the point of comparisons that you should know between capacitor and resistor. Moving on to when you have got capacitors in parallel. If you have got capacitors in parallel, then all of them will be connected across the same potential drop. All of them will be connected across the same potential drop. So this is what capacitors connected in parallel look like. Now, if you wish to replace all these capacitors in parallel and wish to place a single capacitor, then what has to be the equivalent capacitance of all these capacitors connected in parallel? So the formula of capacitors in parallel looks like that of resistors in series. So you will say that C equivalent is nothing but C1 plus C2 plus C3 and so on. Now the same things which I said about resistors in series can be used. If you have got multiple capacitors connected in parallel, let's say of 2 farad, 6 farad, 22 farad, then you know that when you find the equivalent capacitance, you are just going to add up all the capacitance. So the equivalent capacitance has to be more than the greatest of all the capacitor. This is the first thing. Second, if you have got n identical resistors, each of resistance R connected in series, what is the equivalent resistance? So you will say that the equivalent resistance is NR. Similarly, if you have got n identical capacitors, each of capacitance C connected in parallel, then the equivalent capacitance comes out to be C plus C plus C plus C plus C. How many times? N times. So the equivalent capacitance comes out to be NC. The same arguments can be used here as well. So just remember that capacitance in series like resistance in parallel, capacitance in parallel like resistances in series. Now here I want to emphasize on two more important points. When capacitors are in series, what is same? So the charge flow through them is same. And if none of the capacitor has any initial charge, then you can say that the charge at any given instant on all of them is going to be same. Okay. So tell me, across which of these capacitors you will find more potential drop? Sir, from Q equals to CV, all of them have same charge when they are connected in series. Yes, when they are connected in series, all of them have same charge. So potential drop equals to Q by C. The capacitor of lower capacitance will have a higher potential drop across it. To make you understand more, think of two capacitors of 2 farad and 8 farad connected in series. You can see that the second capacitor has got a capacitance 4 times that of first. First one is 2 farad, second one is 8 farad. If the capacitance is 4 times, tell me out of these two, which one will have more potential drop across it? So sir, Q equals to CV. So the potential drop across any capacitor equals to charge on it upon its capacitance. Since the capacitance of second one is 4 times, the potential drop across it will be 1/4. Since the capacitance of second one is 4 times, the potential drop across it is going to be 1/4. So if the potential drop across first one is V, then the potential drop across second one is going to be V by 4. One more thing, if you have got two capacitors connected in series or more than that, now you know that the same charge flows through all of them. Which one will have more energy stored in it? Think of just these two, 2 farad and 8 farad. So you will say that, sir, I know that energy stored inside the capacitor can be written as Q square by 2C, can be written as half CV square, right? Or can be written in other methods as well. For capacitors connected in series, when you are comparing which one has got more energy stored, it's better to use Q square by 2C. Why? Because the charge on all of them is going to be same. So you will say that if I think using energy stored equals to Q square by 2C, the charge on both of them is going to be same, but the second one has 4 times the capacitance. If the second one has 4 times the capacitance, the energy stored in second one will be 1/4 compared to the energy stored in first one. So if the energy stored in first one is U, then the energy stored in second one has to be U by 4. So remember this simple line. In series, more energy is stored and more potential drop across the lower capacitor. Once more, in series, more energy is stored and more potential drop takes place across the lower capacitor. The device which has got lower capacitance, across it you will find more potential drop, and inside it you will find more energy stored. Sir, how can you say? Very simple. For capacitors connected in series, charge is same. Yes. From Q equals to CV, we can say that the potential drop across a capacitor equals to charge by capacitance. So the one which has got lower capacitance, across that the potential drop has to be higher. Moreover, you know that energy stored can be written as Q square by 2C. On all of them, when connected in series, the charge is same. So the one which has got lower capacitance, across it, within it, the energy stored will be higher. Now moving on to capacitors connected in parallel. When capacitors are connected in parallel, what is same? Sir, they are connected across the same potential drop. So from Q equals to CV, for all the capacitors connected in parallel, V is same. So the one capacitor which has got more capacitance will have more charge on it. And thinking of the energy equals to half CV square. Sir, why are you using half CV square rather than Q square by 2C? Because they are connected in parallel. So the potential drop across them is same. That's why it's better to compare using half CV square. So when you connect multiple capacitors in parallel, across all of them, the potential drop is going to be same. So the one which has got more capacitance will have more energy stored inside it. So next point, in parallel, more energy stored and more charge on the higher capacitor. When connected in parallel, more energy stored. From Q equals to CV, V is same. The one which has got more capacitance has more charge and more charge on higher capacitor. So energy stored is half CV square, V is same. The one which has got more capacitance has got more charge on it. So now let's talk about some important points. The first thing, if you have got these three capacitors C1, C2, C3 connected in series, we know that the same charge will flow through them. Yes, sir. And let's say the potential drop across them is delta V1, delta V2, delta V3, and the potential drop across the entire system to be V. We can say that the charge that will flow through this combination has to be equal to the equivalent capacitance of the combination multiplied by the potential drop across the system. So you will say that the charge flow has to be C equivalent, the equivalent capacitance of the system of these three capacitors multiplied by the potential drop across the system. Now, how to find the C equivalent? So they are connected in series. So 1 upon C equivalent will be equals to 1 by C1 plus 1 by C2 plus 1 by C3. When you have got capacitors in series, what is same for all of them? So the charge on all of them is going to be same. Now, you can find the charge using C equivalent into V. And once you have found the charge, you can say that the potential drop across the first capacitance has to be nothing but the charge on it divided by its capacitance. Sir, how can you say Q equals to CV? The charge on the first capacitor has to be equals to C1 into V1. So sir, why you haven't written here Q1? Because beta, the charge on all three of them is going to be same. That is going to be C equivalent into V. So you can say that the potential drop across the first capacitor has to be nothing but the charge on it divided by C1. Why I am using the term charge on it? Because the charge on all three is going to be same. And in place of Q, you can write C equivalent into V. So you can say the potential drop across the first capacitor equals to C equivalent into V divided by C1. Similarly, the potential drop across second capacitor equals to charge on it, which has to be same for all three, divided by its capacitance C2. That can be written as C equivalent into V by C2. And on the third one, you can write the potential drop has to be the charge on it divided by C3. That will be equals to C equivalent into V by C3. Now, if you have got capacitors connected in parallel, and let's say a charge Q enters into the system, first thing which I can say is that this charge gets divided over three capacitors. When capacitors are connected in parallel, the potential drop across them is going to be same. And I can say here two things. First, the potential drop across C1 has to be same as potential drop across C2 has to be same as potential drop across C3. And if the charge on first one going is Q1, the charge going to second one is Q2, the charge going to third one is Q3, then Q has to be equals to Q1 plus Q2 plus Q3. Now, we can say that Q has to be equals to Q1 plus Q2 plus Q3. Yes, sir. Let's say the potential drop across this whole combination is delta V. And the equivalent capacitance of these three capacitors, which will be nothing but C1 plus C2 plus C3, is C equivalent. So can I say that the charge flow into the system has to be equal to the equivalent capacitance of the system multiplied by the potential drop across the system? So we can say the charge flow into the system Q equals to C equivalent into delta V. Or we can rearrange and write the potential drop has to be nothing but the charge flow into the system divided by C equivalent. Now, I know that the potential drop across all three of them has to be same. So the potential drop across the first capacitor also have to be delta V. And from Q1 equals to C1 into delta V, I can say that Q1 will be C1 delta V. In place of delta V, I can write the whole charge entering the parallel combination divided by the C equivalent for the whole system. So in place of delta V, substituting this, we get Q1 equals to C1 Q by C equivalent. Now, what is C equivalent in this case? C1 plus C2 plus C3. For the second capacitor, the charge on it can be written as its capacitance times the potential drop. And the potential drop will be nothing but the charge on the entire system upon the equivalent capacitance of entire system. So that will be C2Q by C equivalent. Similarly, on the third capacitor, the charge will be C3 into delta V. In place of delta V, we can again write Q upon C equivalent. So you get C3Q upon C equivalent. That will be C3Q upon C1 plus C2 plus C3. That's how easy it is. But usually you do not have to work with three capacitors. You have to work with two capacitors. So let's look at the next important points. If you have got two capacitors connected in parallel, they have got capacitance C1 and C2 and a charge Q enters into the system. What will be the charge on the first capacitor? What will be the charge on the second capacitor? So we say that what we have just learned, if you have got multiple capacitors C1, C2, C3, and I will place one more C4. Okay. And if a charge Q enters, then the charge on first capacitor is C1 Q by C1 plus C2 plus C3 plus C4. And similarly, the charge on second one is C2q upon C1 plus C2 plus C3 plus C4 and so on. C1q upon C equivalent. That is the formula. So the charge on this first capacitor will be nothing but C1q by C1 plus C2, since there are only two capacitors, and the charge on second capacitor of capacitance C2 will be nothing but C2q by C1 plus C2. So this is something you should be able to do really fast. Now let's say they have given us that there are two capacitors of capacitance C1 and C2 connected in series. Now the potential here is V1, the potential here is V2. How can you find the potential at the midpoint between the two capacitors? How to find the potential of this point? So we can write an equation. I can say that let's say the potential of this point is V dash. Since both of them are connected in series, whatever charge flows through the first one, the same amount of charge should flow through the second one. And we know that Q equals to CV, where V represents the potential drop across the capacitor. So you can say the charge flow through the first capacitor has to be equals to its capacitance times the potential drop across it. That will be V1 minus V dash. Similarly, this charge flow has to be same even for the second capacitor, and the charge flow through the second capacitor can be written as its capacitance times the potential drop across it, and the potential drop across the second capacitor has to be V dash minus V2. So what you get here is C1V1 minus C1V dash equals to C2V dash minus C2V2. Bringing this C2V2 on the left hand side, you get C1V1 plus C2V2 equals to C1 plus C2 into V dash, or V dash comes out to be C1V1 plus C2V2 upon C1 plus C2. That's all. So easy. So you will say, let's assume the potential of midpoint to be V dash. We can write C1 into V1 minus V dash. What is C1? The first capacitance. What is V1 minus V dash? The potential drop across the first capacitor. And this has to be same as the charge flow through the second capacitor, which will be equals to C2. If here the potential is V dash and there V2, so the charge flow through second capacitor will be C2 into V dash minus V2. So on rearranging the terms, you can write V dash equals to C1V1 plus C2V2 upon C1 plus C2. Easy? So now let's talk about the third important case, and this is really important. They might give you three capacitors of, let's say, capacitance C1, having capacitance C2, and having a capacitance C3. And they will tell you the potential of this point is V1, this point is V2, this point is V3. So how to write an equation to determine the potential at the junction? Because if I can determine the potential at the junction, I can find out the charge on each capacitor, because if I will know potential on both sides of capacitor, I will know the potential difference. And from Q equals to CV, once I know the capacitance and the potential difference, I can find the charge on it. So let's say the charge flow in these three lines is Q1 and Q2 and Q3. I can say from KCL, the charge coming towards the junction has to be same as the charge going away from junction. So the charge coming towards the junction Q1 plus Q2 plus Q3 has to be same as the charge going away from junction, which is 0. So now here we can place three capacitors of capacitance C1, C2, C3. And let's say the potential of these 3 points are V1, V2, V3. Our mission is to find the potential of junction. So we have assumed that, let's say, the charge flowing through the three lines is Q1, Q2 and Q3. And since we know that the charge coming towards the junction has to be same as the charge going away from junction, so Q1 plus Q2 plus Q3 has to be equals to 0. Now simple question, what has to be Q1? So Q1 is the charge flowing through the first capacitor. What will be the charge flowing through the first capacitor? So its capacitance times the potential drop across it. Above the first capacitor, potential is V1. Below the first capacitor, potential is V dash. So the potential drop across the first capacitor is V1 minus V dash. Similarly, the charge flow through the second capacitor is Q2. The capacitance is C2 and the potential drop across it is V2 minus V dash. So you can write in place of Q1, Q2, Q3, C1 into V1 minus V dash plus C2 into V2 minus V dash plus C3 into V3 minus V dash has to be equals to 0. The sum of these three charges have to be 0. So you can bring on opening a bracket C1 into V dash to right hand side, it becomes positive. Similarly, C2 into minus V dash to right hand side and C3 into minus V dash to right hand side. And on the left hand side, you have got C1 V1 plus C2 V2 plus C3 V3. And this is equals to C1 plus C2 plus C3 into V dash. So you have got the potential at the junction V dash equals to C1 V1 plus C2 V2 plus C3 V3 upon C1 plus C2 plus C3. So on solving this, you get V dash equals to C1 V1 plus C2 V2 plus C3 V3 upon C1 plus C2 plus C3. A symmetric result to remember. So for two capacitors, I get C1 V1 plus C2 V2 upon C1 plus C2. Okay. For three capacitors, I get C1 V1 plus C2 V2 plus C3 V3 upon C1 plus C2 plus C3. Easy to remember. Let's move on and see the important case of dielectric and polarization. Now, there are something called polar molecules. Sir, what is the meaning of polar molecules? The molecules which have some dipole moment. If we have got an HCl molecule, then we know that chlorine is more electronegative than hydrogen. So it has got partially negative charge while hydrogen has got partially positive charge. In physics, rather than drawing this every time, we draw something called their dipole moment. The direction of dipole moment is from negative charge to positive charge. A physicist always moves towards positivity in life. So rather than every time drawing a molecule, I will just draw a dipole. What does this dipole mean? Sir, it represents the direction of dipole moment. The tail represents the negative charge, the head represents the positive charge. Now let's say you have a crystal of polar substance. Polar substance means every single molecule have some dipole moment. In the absence of external electric field, all the dipole moments point in random direction, and as we know that dipole moment is a vector quantity and all the dipole moments point in random direction, they cancel out each other's dipole moment. So in the absence of external electric field, we say that the net dipole moment of the crystal of polar substance is zero. The net dipole moment of crystal of polar substance is zero. I am not saying that the dipole moment of each molecule is zero. No, the net dipole moment of crystal of polar substance is zero because all the dipole moments point in random direction, and when you find the net dipole moment, because of the law of averages, they cancel out and the net dipole moment becomes zero. But if we establish an electric field, let's say towards right, then we have learned that a freely suspended dipole always try to align in the direction of field. Why? Because when the dipole aligns in the direction of field, it is in stable equilibrium. The potential energy is minimum equals to minus PE, and that's the state it want to be in the stable equilibrium, in the stable state. So remember that a freely suspended dipole always try to align itself in the direction of field. So if we apply an electric field, let's say towards right, the dipole starts to align in the direction of field, and because of the alignment of all these dipoles, something strange happens. Now what happens here is, you can see all the heads are on one of the side. Why? Because sir, the electric field will push all the positive charge in its direction and all the negative charge in the direction opposite to field. So on the surface, in direction of field, you get accumulation of all the heads, means all the positive charge. And on the other extreme, you will get all the tails, that is all the negative charges. So due to the application of this electric field, you get a net concentration of positive charge on one side and net concentration of negative charge on other side, and due to these induced positive and negative charges, you get an induced electric field within the crystal from the direction of positive charge towards the negative charge. So if now somebody asks you what is the net electric field at a point inside this crystal, so you will say this is a polar substance, right? So when you place an electric field, a freely suspended dipole tries to align itself in the direction of field. Due to the alignment of dipoles, one surface gets positive charge, one surface gets negative charge, and within the crystal, an induced electric field is created due to the charge accumulation on its surfaces. Now the direction of this induced electric field will be opposite to the external because it will be from positive charge towards negative charge. So you will say that the net electric field inside now will be equal to the electric field applied E minus the electric field induced. The net electric field inside equals to electric field applied, the external electric field minus the electric field induced. And we have even learned that when you have got two charges placed inside a dielectric, placed inside a medium of relative permittivity ER, the force becomes ER times smaller. Why? Because the net electric field due to the first charge at position of second charge becomes ER times smaller. So you need to remember that the net electric field inside the crystal is nothing but the electric field applied divided by the dielectric constant. Remember that the dielectric constant and relative permittivity are synonyms. They are one and the same thing. Dielectric constant and relative permittivity are synonyms. So the net electric field inside equals to the applied electric field divided by the dielectric constant, which is K. Now, once you know that the net electric field inside is K times smaller, think of it this way. If you have a material of dielectric constant 2, so if you wish to create at this point an electric field of 20 Newton per Coulomb, the electric field net here created will be half of what you tried to create. So that will be 10 Newton per Coulomb. The electric field net inside equals to electric field that you wish to apply at the point divided by the dielectric constant. So sir, if a medium has got, let's say, dielectric constant of 80, then if you place it in an external electric field E, then at a point inside it, the electric field will be E by 80 times. Yes, that's what I'm trying to say here. So the net electric field inside equals to the electric field you are trying to apply divided by the dielectric constant. So K is called the dielectric constant, which is the synonym of relative permittivity. So for conductors, what has to be the value of dielectric constant? We have learned that under steady state, in the flesh of a conductor, the net electric field is 0. So if you place a conductor in an external electric field E, then at a point inside it, the net electric field comes out to be 0. So what has to be the value of K for a conductor? Sir, if you want the electric field inside to be 0, this means that E by K has to be 0. This means that K has to be infinity. So remember that for conductors, the dielectric constant, the relative permittivity, comes out to be infinity. For vacuum, sir, in vacuum you do not have any molecule, yeah, so there will be no alignment. Yes, oh, so if there will be no alignment, then the electric field inside has to be same as the electric field you are trying to apply. Yes, so the electric field inside will be same as the electric field you are trying to apply. So both of them will be equal. So E equals to E by K. So K has to be equals to 1. So for vacuum, the dielectric constant or relative permittivity comes out to be 1. So what we need to remember here, first, the electric field net inside equals to electric field that you are trying to apply divided by the dielectric constant or relative permittivity. For conductors, since E net inside comes out to be 0, for conductors the dielectric constant is infinity. For vacuum, since there is no substance in vacuum, if you take a container with nothing in it and then you try to apply some electric field, let's say having some external source at a point inside it, then the electric field you are trying to apply won't be opposed by any type of induced charges. So the electric field will be same. Hence the dielectric constant for vacuum has to be 1. So remember that for all materials, the dielectric constant is greater than equal to 1. Only for vacuum you get the dielectric constant to be equal to 1. All materials have got dielectric constant greater than 1. Now as you see that for all substances dielectric constant is greater than equal to 1. Here comes a legitimate doubt in your mind. Sir, what you have just taught is for polar substances, but all substances are not polar. How can in non-polar substances you can have some induced electric field? Because here comes the key concept. Even when you place non-polar substances in an external electric field, they become polar. Think of a non-polar substance. So in a non-polar substance, let's say you have got a positive charge and there is an electron cloud around it. The center of charge of this electron cloud will be at the center. So there is no separation between the positive and the negative charge. Hence the dipole moment is 0. But if you place this polar substance in an electric field, on the electron cloud there is a force in direction opposite to the electric field. On the positive charge, there is a force in direction of field. So because of this, a separation takes place between the center of charges. So you find something like this: the positive shift in direction of field while the negative shifts in direction opposite to field, and now there is some separation between the positive and negative charge, and now you have some dipole moment. So remember that even a non-polar substance, when placed in an electric field, becomes polar, and once it becomes polar, it produces an induced electric field, because of which the net electric field inside comes out to be less than the external applied electric field, because of which the value of K comes out to be more than 1, because the inside electric field is less than the external. So now let's talk about induced charges on a sheet. Sir, what is the meaning of this? We have learned till now that if we place a dielectric in an external electric field, in the direction of field, the positive charges experiences a force. So let's say on this side, on this surface of the sheet, we get a positive charge accumulation plus Q. And on the opposite surface, we get a negative charge accumulation minus Q. Our mission is to find what will be the magnitude of this Q, assuming the sheet to be infinitely large. Now we know that due to the positive charge at a point inside the dielectric, the positive charge will produce field away from it, that is towards left, while the negative charge will produce at the same point field towards it, that is again towards left. So both the charge accumulation on the two surfaces produces a field in direction opposite to the applied. So the applied electric field is towards right and the induced electric field is towards left. That's why we say that the net electric field inside equals to the applied electric field minus the electric field due to the induced charges. We can use this particular relation to determine how much charge will be accumulated. How? Let's see. First, you need to focus that if you have an infinitely large plane sheet having a charge per unit area sigma, where sigma is the charge per unit area, you get an electric field produced by it, and this electric field is sigma by 2 epsilon naught, that will be equals to Q by A upon 2 epsilon naught, right? Now you can say that the electric field produced by these two charges distributed over the surface area will be equals to Q by A upon 2 epsilon naught due to, let's say, the positive plate, plus a field of same magnitude in the same direction, Q by A upon 2 epsilon naught, let's say towards the negative plate. So the net electric field produced due to the induced charges on the two surfaces will be nothing but the sum of these two fields, which will be Q by A epsilon naught. We know that the net electric field inside will be nothing but the electric field applied minus the electric field induced. And we know that the net electric field inside is nothing but the electric field applied upon the dielectric constant. So this has to be equals to E by K. Now substituting the value of induced electric field, we can find out what will be the charge accumulation on the surface. So substituting the value, we get E minus Q by A epsilon naught equals to E by K. On rearranging the terms, we can write Q by A epsilon naught equals to E minus E by K, and then you can take E common. So you will write Q by A epsilon naught equals to E times 1 minus 1 by K. And then bringing this A epsilon naught to the right hand side, you will say that the charge induced on the surface equals to E A epsilon naught, the applied electric field into the surface area into epsilon naught, into 1 minus 1 by K, where K is the dielectric constant, also called the relative permittivity. So now let's learn what happens when we insert a dielectric inside a capacitor. So let's say we have parallel plate capacitor and we fill the entire space between the plates of this parallel plate capacitor with a dielectric. So the entire space has been filled with a dielectric. We know that if you create an external electric field E, then the field within the dielectric is nothing but E upon K. So visualize that you have got these two plates of parallel plate capacitor, the left plate having a charge plus Q, the right plate having a charge minus Q. And here in the entire region between the plates, we have inserted a dielectric of dielectric constant K. The separation between the plates is D and the plate area is A. Our mission is to find what is the capacitance of the system after insertion of dielectric. So we will say that in the absence of this dielectric, We know that the electric field between the plate will be equals to Q upon epsilon naught A, in which both the plates contribute equally. Now once the dielectric has been inserted, the net electric field between the plate within the dielectric becomes K times smaller. So we will say that electric field has to be equals to 1 by K times Q upon epsilon naught A. This part would have been the field between the plates if there would have been no dielectric. But since we have placed a dielectric and we know that within the dielectric the field becomes K times weaker, that's why we are writing electric field between the plates within the dielectric to be equals to 1 by K times Q upon epsilon naught A. Once you know what is the electric field between the plates within the dielectric, game over. Now you can say the potential drop has to be equal to nothing but the electric field times the distance between the plate, and this electric field is nothing but Q upon K epsilon naught A. So substituting that, you get what is the potential drop. We know that Q equals to something times delta V, and that something is our capacitance. So rearrange this and write Q equals to K epsilon naught A by D into delta V. Now you know that epsilon naught A by D is the capacitance of the parallel plate capacitor when you do not place any dielectric. If you have completely filled the region between the plates with a dielectric, then the field becomes K times weaker, the potential drop becomes K times smaller, and as the potential drop becomes K times smaller, for the same charge, you say that the capacitance becomes K times larger. So if you fill up the plate with a dielectric of dielectric constant K, then the capacitance becomes K times. So in the absence of dielectric, the capacitance was epsilon naught A by D. On inserting the dielectric, it becomes K times epsilon naught A by D, right? So you will say that the capacitance in this case has to be equals to K times epsilon naught A by D, which is K times the capacitance without the dielectric. So we write one equation, and we write the equation as capacitance with dielectric. In the subscript, we have written K equals to dielectric constant times capacitance without the dielectric. Now let's understand terms one by one. Ck is the capacitance when completely filled with a dielectric of dielectric constant K. What is K? The dielectric constant. And what is C? C is the capacitance without the dielectric when you have got vacuum between the plates. For vacuum, the dielectric constant is 1. That's why if here you substitute the value of K as 1, you will get the same capacitance as of vacuum, right? So let's move on. So one can say that the capacitance with dielectric equals to the dielectric constant times the capacitance without dielectric. But this formula works only when the entire region between the plates is filled with a dielectric. But what if you have got multiple mediums filled between the plates and they do not completely fill up the space? For example, let's say you have got these two plates, okay? And between these two plates, you have got multiple infinitely large slabs, very large slabs of thickness T1. I am drawing the side view. Think of slabs between the plates. Thickness T1 and thickness T2, made up of material of dielectric constant K1 and K2. And let's say the plate separation is T. Now how to find the capacitance in this case? So let's learn this case now. Capacitor with multiple sheets between the plates. So let's say you have got this case. The positive plate has a charge plus Q, the negative plate has a charge minus Q, and let's say the plate area is A. The separation between the two plates is D, and you have placed two dielectric slabs of thickness T1 and T2 having dielectric constant K1 and K2. We know that at point A, C and E, which are in the region outside the dielectric, the electric field will be same as the electric field that these two infinitely large sheets want to create, which is Q upon epsilon naught A. Inside the first dielectric, let's say at a point B, which is inside the first dielectric, the electric field will be K1 times smaller. So you will say that electric field at point B will be 1 by K1 times Q upon epsilon naught A. The electric field at a point inside the second dielectric, which has got dielectric constant of K2, will be equals to electric field at point D will be 1 by K2 times the applied electric field, which is Q upon epsilon naught A. So one can say that electric field at point A, which is outside the dielectric, is same as electric field at point C, which is again outside the dielectric, is same as the electric field at point E, and which is equals to Q upon epsilon naught A. While the electric field at point B will be K1 times smaller than Q upon epsilon naught A. So electric field at point B will be Q upon K1 epsilon naught A, and the electric field at point D will be equals to Q upon K2 epsilon naught A. Now, how to find the capacitance of this system? So, same process. Go from the left plate to the right plate, and going from left plate to right plate, look at the potential drop. Look at the potential drop and write that potential drop in terms of charge. Then rearrange it and write Q equals to something times delta V, and that something will be your capacitance. So, in this region, let's say in the region of thickness X, you will say that the potential drop will be equal to the electric field here, which is Q by epsilon naught A into X. In this next thickness T1, the potential drop will be equal to the electric field within the first slab, that will be Q upon K1 epsilon naught A multiplied by its thickness T1. The potential drop going from here to here in the region where the point C lies, you will say that the potential drop has to be equal to electric field in this region multiplied by Y, and the electric field in this region is Q upon epsilon naught A. Going within the second slab, you will say that the potential drop will be equal to the electric field inside the second slab multiplied by its thickness T2, and going in this last region where the point E lies, you will say that the potential drop has to be electric field in this region, which is Q upon epsilon naught A, into its thickness, which has been taken as Z. So you will say that the overall potential drop will be Q upon epsilon naught A electric field here multiplied by thickness X plus Q upon K1 epsilon naught A into T1 plus Q upon epsilon naught A into Y plus Q upon K2, here should be K2 epsilon naught A into T2 plus Q upon epsilon naught A into Z. So this is how you can write the overall potential drop. Now take Q common and write delta V as Q upon epsilon naught A times X plus Y plus Z plus X plus Y plus Z from these three terms plus T1 by K1 from this term plus T2 by K2. Here has to be K2. That's what you get. Now once you have written this, rearrange it as Q equals to something times delta V, and that something will be your capacitance. So you will get delta V equals to Q by epsilon naught A. In place of X plus Y plus Z, in place of X plus Y plus Z, can you write D minus T1 minus T2? D minus T1 minus T2. Can I say that X plus T1 plus Y plus T2 plus Z equals to D? Yes, sir. So can I write that X plus Y plus Z equals to D minus T1 minus T2? Yes. So that's what has been written here in place of X plus Y plus Z. Now once you have written it this way, rearrange it as Q equals to something times delta V. The epsilon naught A goes up. This D minus T1 minus T2 plus T1 by K1 plus T2 by K2 comes down. So you get Q equals to something times delta V. So this something has to be your capacitance. So if you have got a parallel plate capacitor with the place separation D and the plate area A, and you place in two dielectrics between the plates of thickness T1 and T2 having dielectric constant K1 and K2, then you say that the capacitance comes out to be epsilon naught A upon D minus T1 minus T2 plus T1 by K1 plus T2 by K2. This is the formula to remember the capacitance. Sir, do I need to remember this formula? Yes, very much. Why? Because it's very useful. Let's see some examples based on this particular formula, and it's an important formula. Sir, if rather than having two plates, we have got three slabs, what to do? Better then here you will get D minus T1 minus T2 minus T3 plus T1 by K1 plus T2 by K2 plus T3 by K3. If you have 4, do the same thing. D minus T1 minus T2 minus T3 minus T4 plus T1 by K1 plus T2 by K2 plus T3 by K3 plus T4 by K4. That's all. So let's see one example. The question goes like, if on inserting a dielectric of thickness D by 3, so if the plate separation is D, you have placed a dielectric of thickness D by 3, the capacitance becomes 5 by 4 times. So if the original capacitance before inserting the dielectric was C, the new capacitance, say C dash, is 5 by 4 times of C. Then determine the dielectric constant of this material. That's our mission. Let's do it. You will say that the initial capacitance before you have inserted the dielectric, when this parallel plate capacitor was empty, will be equal to epsilon naught A by D. We have mucked up this formula. Now on inserting a dielectric medium of, let's say, dielectric constant K having a thickness D by 3, the new capacitance will be, let's say, C dash, and this, the final capacitance, will be equals to epsilon naught A upon D minus D by 3 plus D by 3K. So this will be your new capacitance. Now D minus D by 3 gives you 2D by 3. And we know that this new capacitance is 5 by 4 times of original, where original capacitance is epsilon naught A by D. So you can write epsilon naught A upon, take the D common, you get 1 minus 1 by 3, that gives you 2 by 3. And if you take D outside from here, you are left with 1 by 3K. Now this new capacitance is 5 by 4 times the original capacitance, which is epsilon naught A by D. So it will cancel out epsilon naught A by D, epsilon naught A by D. So what you get from here is, on cross multiplying, 5 by 4 equals to 1 upon 2 by 3 plus 1 by 3K. On cross multiplying here, you get 5 into 2 by 3 plus 1 by 3K equals to 4. And then you need to solve it to get K. So you can rewrite it as, bring the 4 up, equals to 5 times of 2 by 3 plus 1 by 3K. Now open up this bracket. So you get 4 equals to 5 into 2 by 3, that gives you 10 by 3, plus 5 into 1 by 3K, that gives you 5 by 3K. So rearrange it, bring this term to left hand side. So you get 5 by 3K equals to 4 minus 10 by 3. Now once you get 4 minus 10 by 3, that is 12 minus 10 by 3, that becomes 2 by 3. So you get 5 by 3K equals to 2 by 3. Cancel out bacho, 3 and 3, bring the K up and the 2 down. So you get K equals to 5 by 2. Once you know that K is 5 by 2, that can be written as 2.5. So this is one example based on the formula I have just taught you. If you have got a parallel plate capacitor with multiple plates of thickness T1, T2, dielectric constant K1, K2, then the capacitance comes out to be epsilon naught A upon D minus T1 minus T2 plus T1 by K1 plus T2 by K2 and so on. So let's see next example. The next example goes like, on inserting a dielectric of thickness 2 mm in between the plates of a capacitor, the separation between the plates has to be increased by 0.5 mm to keep the capacitance same. So if the original separation was D, after insertion of this dielectric, you have to increase the plate separation by 0.5 mm. You have to make it D plus 0.5 mm to keep the capacitance same. Determine the dielectric constant of the sheet material. So what is the dielectric constant of the sheet material if you have to increase the plate separation by 0.5 mm after insertion of the dielectric? So let's think of the original case. When you have the capacitance empty, and then when you insert a dielectric of thickness 2 mm between the plates, you have to increase the plate separation by 0.5 mm. Then the capacitance is same as the original case. So question is, what is the dielectric constant of this material? So simply you have to write the initial capacitance, you have to write the final capacitance and equate them to get the dielectric constant. Initial capacitance is easy. You will say that the initial capacitance is epsilon naught A by D. Say the final capacitance is C dash. So you will say that the final capacitance C dash equals to epsilon naught A by D plus 0.5, the new plate separation, minus T1, which is 2, plus 2 by K, right? So you will write epsilon naught A upon D plus 0.5, which is the new plate separation. Original was D. Now the plate separation is not D, it is D plus 0.5, minus 2 plus 2 by K. Since you know that these two capacitances are equal, simply equate them. When you equate them, epsilon naught A, get cancelled. So what you get is D equals to D plus 0.5 minus 2 plus 2 by K. So D equals to D plus 0.5 minus 2 plus 2 by K. Cancel out bacho D and D. 0.5 minus 2 gives you minus 1.5, and bring this minus 1.5 to the left hand side, that becomes 1.5. So you get from here 1.5 equals to 2 by k. If you know that 1.5 equals to 2 by k, you can write it as 3 by 2 equals to 2 by k, or the dielectric constant comes out to be 4 by 3, which is 1.33. So the dielectric constant comes out to be 2 by 1.5, which is 4 by 3. Easy. You just need to remember the formula. If the plate separation is d and you have inserted a dielectric sheet of dielectric constant k, then the new capacitance is epsilon naught A upon d minus t plus t by k. This is for single sheet. So now let's see the case of partial insertion of dielectrics. What if I give you a case like this? Here you can see that you have placed two dielectrics of dielectric constant k1 and k2, but you have filled up the entire space between the plates. These two dielectrics have thickness T1 and T2, but the entire space between the plates has been filled up. Now, what will be the capacitance of this system? So you can say, sir, I will use the same formula, epsilon naught A upon D minus T1 minus T2 plus T1 by K1 plus T2 by K2. So the capacitance has to be nothing but epsilon naught A upon D minus T1 minus T2 plus T1 by K1 plus T2 by K2. But since these two slabs fill up the entire space between the capacitor plates, so you can say that the sum of their thickness T1 plus T2 has to be equals to D. If I can say that T1 plus T2 equals to D, this means that D minus T1 minus T2 will be equals to 0. So the capacitance of this system will be nothing but epsilon naught A upon T1 by K1 plus T2 by K2, right? But this is not the case for which I am teaching you this topic. What if you get this type of case? That between the two plates of the capacitor you have filled up two dielectrics, but this way. Such that the upper part, the area A1 is filled with a medium of dielectric constant K1, and the lower part, the area A2 is filled with a medium of dielectric constant K2. Now how to find the capacitance of this system? So you will say, I can think of two capacitors in parallel. The upper capacitor having a plate area A1, the lower capacitor having a plate area A2. The upper capacitor filled up with a dielectric of dielectric constant K1, and the lower capacitor of plate area A2 filled with a dielectric of dielectric constant K2. And I know that the capacitance of this upper capacitor, if it was empty, would be epsilon naught A1 by D. But since you have filled it up with a medium of dielectric constant K1, its capacitance will be K1 epsilon naught A1 by D. And for this second capacitor filled with dielectric of dielectric constant K2, the capacitance will be K2 epsilon naught A2 by D. And how to find the overall capacitance? What do you do when you have got two capacitors C1 and C2 in parallel? The C equivalent is nothing but C1 plus C2. So think that here you do not have one single capacitor. Think that you have got two capacitors in parallel. The upper capacitor of plate area A1, the lower capacitor of plate area A2, both have got separation between the plates equal to D. The upper capacitor filled up with a medium of dielectric constant K1, the lower one filled up with a medium of dielectric constant K2. The capacitance of the upper capacitor formed in such a way will be K1 epsilon naught A1 by D. The capacitance of the lower capacitor formed in such a way will be K2 epsilon naught A2 by D. And the net capacitance will be sum of these two capacitance. So the net capacitance will be nothing but K1 epsilon naught A1 by D plus K2 epsilon naught A2 by D. You can take epsilon naught by D common. You will have K1 A1 plus K2 A2. Easy. So let's move on to practicing some questions based on these two concepts. So the first question goes like, here you have got two plates, and between the two plates you have completely filled up the space with two dielectric slabs. The first slab has got dielectric constant K, the second one has got dielectric constant 2K. The first slab has got thickness D by 3, 1/3 of the separation between the plates, and the second dielectric has a thickness 2D by 3. So question is, if the empty capacitor has a capacitance C, when nothing was filled, the capacitance was C. This means that epsilon naught A by D equals to C. Determine the capacitance for the system after insertion of the two dielectric mediums. So you will say that the capacitance after inserting the dielectrics, let's say it is C dash, will be equal to epsilon naught A upon d minus d by 3 minus 2d by 3 plus d by 3 t1 divided by k1 d by 3 divided by k plus t2 divided by k2, that is 2d by 3 divided by 2k. Let us cancel out this 2 and 2. So what you get is d minus d by 3 minus 2d by 3. This whole part becomes 0. D by 3k plus d by 3k becomes 2d by 3k. So you will write the new capacitance will be epsilon naught A upon d minus d by 3 minus 2d by 3. T1 is d by 3. T2 is 2d by 3 plus T1 by K1 d by 3 divided by K plus T2 by K2 2d by 3 divided by 2K. So here you can cancel out 2 and 2 and this whole part becomes 0. So what you get is C dash equals to epsilon naught A upon d by 3k plus d by 3k. So that becomes epsilon naught A upon 2d by 3k. You can rewrite it as 3k upon 2 times epsilon naught A by d, which is the capacitance of the empty capacitor. So the new capacitance C dash can be written to be equals to 3k by 2 times the original capacitance, which is C. Now they might even ask you, what is the equivalent capacitance of these two? How to write? You will say that rather than filling up with two mediums of two different dielectric constant, I should fill it up with a single medium of how much dielectric constant to get the same equivalent capacitance. So you will say let's fill it up with K dash. This K dash will be the equivalent of these two. So on inserting the entire region with a single slab of dielectric constant K dash, we know that the new capacitance will be K dash into C. So you can say that this equals to K dash into C. So the equivalent dielectric constant comes out to be 3K by 2. This type of questions have also been asked in competitive examinations already. So you should know how to find the equivalent dielectric constant as well. Let's move on to the next example. The question goes like, now you have got again two plates. The entire plate area is A. The upper A by 3 area is filled with a medium of dielectric constant K, and the lower 2/3 area 2A by 3 is filled up with a medium of dielectric constant 2K. Now what will be the capacitance of this system if the capacitance of the empty capacitor was C? So if the empty capacitor has a capacitance C, determine the capacitance for this system. So you will say that I can think of it to be two capacitors in parallel. The upper capacitor having a plate area A by 3, having plate separation D, filled up with a medium of dielectric constant K between the plates. So the capacitance will be nothing but the dielectric constant times epsilon naught times the plate area, which is A by 3 upon D. And for second, you will get the dielectric constant, which is 2K, multiplied by epsilon naught, multiplied by plate area, which is 2A by 3 divided by D. So you will say that the net capacitance will be nothing but the sum of these two capacitance because they are in parallel. So you will say that the net capacitance, let's call it C double dash, equals to K epsilon naught A by 3D plus 4K epsilon naught A by 3D. Now in denominator you have got 3D, here you have got 1, here you have got 4. When you add them up, you get 5K epsilon naught A by 3D. Now in place of this epsilon naught A by D, you can write the original capacitance of the empty capacitor. So you will say that the new capacitance after insertion of these two dielectrics equals to 5K by 3 times the original capacitance. If they ask you what is the equivalent dielectric constant for these two materials, so you will say removing these two materials, if I place a single material of let's say dielectric constant K dash, then what has to be the value of K dash? So you will say that K dash C will be equal to the new capacitance, or K dash, the equivalent dielectric constant on filling up in this way comes out to be 5K by 3. Now let's move on to the next thing we need to talk about, which is insertion of dielectric between the plates. What happens when we insert a dielectric to completely fill up the space between the plates of the capacitor? that the capacitance becomes K times. That's one thing. But what happens to the charge on the plate? What happens to the electric field between the plates? What happens to the force between the plates? Now, this particular part which I am teaching right now is super important. So focus on everything I say here very, very clearly. Now here they will ask you that we have completely filled up the space between the plates of capacitor with a dielectric of dielectric constant K. But they will give you two cases. The first case, when you have an isolated capacitor. So if you have an isolated capacitor, you know that in case of an isolated capacitor, it is not at all connected to anything. If it is not at all connected to anything, the charge can't flow. So for an isolated capacitor, the charge on the capacitor plates remains constant. Now once you fill up a dielectric between the plates, the charge on the plates won't change because it's isolated. It's not connected to anything. So the charge can't go anywhere. So sir, what are we going to do now? We are going to learn how the different properties change. So property, what was old, what was new. So if the original capacitance was C, then after insertion of the dielectric to completely fill up the space, what will be the new capacitance? So sir, capacitance becomes K times the capacitance with the dielectric equals to K times the capacitance without dielectric. So capacitance becomes K times. What happens to the charge? Sir, it's isolated capacitor, not at all connected to anything. So the charge can't go anywhere from the principle of conservation of charge. So if the initial charge on the capacitor plate is Q, then the final charge also on the capacitor plate has to be Q. The next property, what happens to the potential drop across the plate? Now you can think that Q equals to C delta V. Yes sir. For this particular case of isolated capacitor, when you insert the dielectric, the charge remains the same, but the capacitance becomes K times. So the potential drop should become 1 by K times so that the charge remains the same. Or you can think this way, Q equals to C delta V. Yes sir. Delta V equals to Q by C. Yes sir. So the potential drop is inversely proportional to the capacitance as the charge is constant. So if the capacitance becomes K times, then the potential drop becomes 1 by K times. I will give you one more explanation for this. So if the original potential drop between the plate was V, the new potential drop between the plates will be V by K. This is for the case of isolated capacitor. Let's see the next point. What happens to the electric field in the region between the plates? Sir, we already know. In the absence of dielectric medium, the electric field will be equals to Q upon epsilon naught A. But once you have placed a dielectric material, the field becomes K times weaker. So the new electric field between the plates has to be Q upon K epsilon naught A. So if you say that the original strength of electric field between the plate was E, the new strength of electric field between the plate will be E by K. So if the original strength is E, the new strength will be E by K. And this is again from where you can correlate between the original potential drop and the new potential drop. Since we know that potential drop is nothing but electric field strength times the separation between the plates as the electric field is uniform. So when the electric field strength becomes 1 by K times, then on going through the same distance, the potential drop will be 1 by K times because field is nothing but potential gradient. So if the electric field strength becomes 1 by K times, then the potential drop will also become 1 by K times on going through the same distance. Now, the next point, what happens to the force between the plates? How did we derive the formula of force between the plates? Sir, you said that the force between the plates equals to the field strength due to first plate at position of second plate, which is Q upon 2 epsilon naught A multiplied by the charge on the second plate. Now, many a times students think that this field becomes 1 by K times. No. Is the second plate inside the dielectric? No. Is the second plate outside the dielectric? Yes. Since the second plate is outside the dielectric, the electric field produced by first plate at the position of second plate remains the same given that the charge on first plate remains the same. And in this case, since the plates are isolated, the charge on them remains the same. Do understand that the second plate is not inside the dielectric. It is outside it. So at that point, the field produced by the first plate remains the same, equals to Q upon 2 epsilon naught A, multiplied by the charge on the second plate, which also remains the same. So that's why the force do not change at all. So you will say if the original force was F, the new force is also F. Many a times students do this error and they mark that the new force should be F by K, because the field due to the first plate at the position of second plate becomes 1 by K times. No, that is wrong. Why? Because the second plate is outside the dielectric. At the position of second plate, the field due to first plate remains the same, equals to Q upon 2A epsilon naught. Let's move on to the next part. What happens to the energy stored? Sir, let's see using energy stored equals to Q square by 2C. Okay. Sir, why are you using Q square by 2C? Why not half CV square? Because better in the case of isolated plate, the charge remains the same. So it's better to look from Q square by 2C. Okay, sir. So since the charge remains the same, but the capacitance becomes K times, the energy stored becomes 1 by K times. It is inversely proportional to the capacitance for same charge. So you will say that the energy stored, if initially it was U, the new energy stored after insertion of the dielectric will be U by K, comparing using Q square by 2C. Now I said that this particular heading is important. If you missed up on any of the part, please listen to it carefully again. Now let's move on to the second case when the capacitor is connected to a battery. So let's say you have got this capacitor connected to a battery of potential V. We know that the charge on the capacitor will be equals to capacitance times the potential drop across its plate. If you have connected it to a battery of potential V, then the potential drop across the plate of capacitor will also be V. Now we have inserted a dielectric between the plates. So when we have inserted a dielectric of, let's say, dielectric constant K between the plates, what will be the new capacitance? So we know that capacitance with the dielectric equals to K times the capacitance without the dielectric, given that the dielectric completely fills up the space between the plates. Now let's compare the old properties with the new properties. So first of all, capacitance. Sir, capacitance depends upon three things: shape, size, and material. Because on material depends the dielectric constant. It does not depend upon the charge given. It does not depend upon the applied potential drop. Since here the material between the plates has been replaced from vacuum and now you have placed a material of dielectric constant K, I will simply say the capacitance becomes K times. So if the original capacitance was C, the new capacitance will be Kc. That's all. Now let's talk about the charge. Sir, see, when you connect a capacitor of capacitance C to a battery which produces a potential drop V across its plate, then the charge on the capacitor will be CV, Q equals to CV. And now when you have inserted a medium of dielectric constant K, the new charge on the capacitor plate will be the new capacitance Kc into V and minus Kcv. So the charge which was originally Cv will now be equals to Kcv. So the charge on the capacitor plate becomes K times. So you will say original charge was Cv and the new charge will be Kcv. The next point, what happens to the potential drop across the plates of the capacitor? You have connected the capacitor to a battery. The battery will maintain a potential drop V across its terminals. So the same will be the potential drop across the plates of capacitor. So if the original potential drop was V, the new potential drop will also be V. Next, what about the electric field between the plates of the capacitor? So you will say that electric field between the plates. Electric field between the plates of the capacitor is given by Q upon epsilon naught A. Yes, sir. In the first case, since you know that the charge will be Cv and minus Cv, in the first case, the electric field between the plates will be Cv upon epsilon naught A. This is the initial electric field. What will be the electric field between the plates after insertion of dielectric? So you will say, sir, after insertion of dielectric, since the capacitance becomes K times, the charge becomes K times and the new charge is KCV. So the new electric field will be KCV, the new charge, upon epsilon naught A. Right? Wrong. Why? Sir, this dielectric medium will again make the electric field K times smaller. So the charge of KCV will try to produce an electric field between the plates equals to KCV upon epsilon naught A. But due to the presence of dielectric medium, the field will become K times weaker. So again, you have to divide it with a K. So you get that the new electric field is same as the original electric field. Sir, I did not get it. I have got one more way to explain it to you. Is the potential drop initially same as the potential drop finally? Yes, sir. Can I write that potential drop is field times distance? Yes, sir. Does the potential drop between the plates changes in this case? No, because it's connected to a battery. Do the plate separation change? No. Since electric field can also be written as the potential drop upon D. Since the potential drop is same and the plate separation is same, the electric field strength remains the same. So if between the plates original electric field was E, the new electric field will also be E. So keep this in mind. This is an important point. Students do it wrong all the time. Once more, I will give you the first explanation. The potential drop remains the same, yes, but the capacitance becomes K times. So the charge becomes K times. Due to K times the charge, after insertion of dielectric, the field will try to be K times, but since you are looking at the points inside the dielectric medium, the field again becomes K times weaker and hence you end up getting the same electric field strength. So this is something important. Students do it wrong all the time. Keep your mind on this. The next one, what happens to the force between the plates? So sir, we know that the force between the plates is given by Q upon 2 epsilon naught A multiplied by the charge on the second plate. So that gives you Q square upon 2 epsilon naught A. Do remember that the second plate is outside the dielectric. The second plate is not inside it. So the field strength produced by the first plate at position of second plate remains equals to Q upon 2 epsilon naught A. Now since the charge becomes K times, if the original charge was CV, which is Q, the new charge will be KCV, which will be KQ. And you know that the force is proportional to Q square. If the force is proportional to Q square and the charge become K times, then you will say that the force will become K squared times. So if the original force was F, the new force will be K square F. Students do this one also wrong all the time. So focus on this one and its argument. Now comes the last one, which is quite easy. What happens to the energy stored? This time I will compare using the energy stored within the plates, between the plates of capacitor to be half CV square. So we will say that since the potential drop is same, but the capacitance becomes K times, the energy stored will become K times. So if the original energy stored was U, the new energy stored will be nothing but KU. So I have said this already, the points which I have told here, one of the part will be asked as your objective question. So in a way, think that we have covered 1, 2, 3, 4, 5, 6, 6 into 2, 12 questions right here. And they are important. If you haven't understood any part, go through the video again. It will help you remember the results. Moving on to the next case, energy loss on charging a capacitor. If you take a capacitor of capacitance C and connect it to a battery of potential V, once you turn the key on, what happens? Sir, some charge flows from the battery to the capacitor. How much charge? Sir, initial charge on the capacitor is 0, 0, and now some charge will flow, and we know that the charge found on the capacitor plate will be nothing but its capacitance times the potential drop across the plate. So we know that a charge Q will flow through the battery, and this charge Q will be nothing but equals to CV. So the charge on the positive plate will be plus CV, the charge on the negative plate will be minus CV. Now here I am going to ask you two questions. When you charge a capacitor, what is the change in internal energy? What is the change in the energy stored in the form of electric field between the plates of capacitor? So you will say, sir, initially there is no charge. So the initial energy stored is 0. And we know that since finally we have a capacitor of capacitance C across whose plates we have a potential drop V, the final energy stored will be half CV square. So you will say that the change in energy of the capacitor will be final half CV square minus initial 0, that is half CV square. Now what will be the work done by battery? We know that when the battery moves a charge Q across a potential drop delta V, then the work done by the battery is given by Q delta V, the charge it has moved multiplied by the potential drop through which the charge has been moved. This is the basic definition of potential. So the work done by battery will be equals to QV. Here V represents the potential drop across the terminals of the battery. Now the charge that will move equals to CV. So the work done by battery will be CV into V, and CV into V gives you CV square. So notice that the work done by battery in the process is CV square, but the energy stored in the capacitor is only half CV square. So what happens to the other half CV square? It gets lost. If they place a resistor here and ask you what is the energy lost through this resistor, you will say that the energy lost through this resistor is half CV square, because battery does a work of CV square, but only 50% of it, only half of it gets stored inside the capacitor. So the other half gets lost in the form of heat or unaccounted losses. So 50% of the work done by the battery is stored in the capacitor in the form of internal energy. Only 50% of the work done by the battery is stored in the capacitor in the form of internal energy. So let's see the last example for the hour, and we will talk more on capacitor in the next hour. So question is, here you have a capacitor connected already with a battery of potential V. Keeping the capacitor connected to battery, if a dielectric of dielectric constant K is inserted, find what will be the charge flow through the battery, what will be the change in energy stored inside the capacitor, and what will be the work done by the battery. So you will say, originally the capacitor is connected with the battery of potential drop V. So initially the charge on the capacitor plates will be CV and minus CV. Once we have inserted a dielectric of dielectric constant K, the capacitance becomes Kc and the charge on the plates becomes KCV and minus KCV. So do understand that originally the charge was CV. Now after insertion of dielectric, the charge is KCV. So question is, how much extra charge must have flown from the battery to the capacitor plate to increase the charge on the plates from CV to KCV? So you will say that the charge flow has to be equals to the final charge on the capacitor plate minus the initial charge. The final charge on the capacitor plate is KCV. Initial charge on the plates is CV. So how much extra charge must have flown through the battery? So you will say that has to be KCV minus CV. You can take the CV common and you will write the extra charge that must have moved has to be nothing but K minus 1 into CV. Okay. The second part. What is the change in the energy stored between the plates of capacitor in the form of electric field? So you will say that the change in energy stored will be nothing but the final energy stored minus the initial energy stored. The final energy stored will be half into Kc, the new capacitance, into V square, minus the initial energy stored, which is half CV square. So once you write this, you can take half CV square common and you will get K minus 1. So you will get half into K minus 1 into CV square. This will be the change in the energy stored between the plates of capacitor. The last part of the question, what is the work done by the battery? The work done by the battery will be nothing but the charge flow, how much extra charge has flown, which is K minus 1 into CV, multiplied by the potential drop across the terminals of battery. So work done by battery equals to the excess charge that flows multiplied by potential drop between the plates. So the excess charge that flows is K minus 1 into CV multiplied by the potential drop across its terminal V. So what you get here is K minus 1 CV square. I want you to notice this again, only 50% of the work done by battery, only 50% of the work done by battery is stored as energy between the plates of the capacitor. So that's all in this hour. See you guys in the next hour where we will talk more about capacitors. See you guys. Bye bye. So that's all for now. See you guys in the next hour.